Hello and welcome back. I'm glad you found your way here again tonight. Tonight we're leaving the ground behind altogether, drifting up past the clouds, past the reach of any airplane, out into the quiet dark, where our small blue planet is, just one of many worlds orbiting a single, ordinary star. Tonight's journey is through the solar system, the sun, the planets, the moons, and the vast, cold emptiness that holds them all together. If this is your first time here, consider subscribing to Drowsy with Facts, where every episode is 100 gentle facts, softly narrated, designed to carry you all the way to sleep. For now, let's begin. At the center of everything we're about to explore sits the sun, and it's worth starting there because almost nothing in the solar system makes sense without it. The sun is not simply the brightest thing in our sky. It is, by an overwhelming margin, the most massive object for billions of miles in any direction. It holds more than 99% of all the mass in the entire solar system. If you imagine every planet, every moon, every asteroid and comet gathered together into one great pile, the sun would still outweigh that pile more than 1,000 times over. Its gravity is the reason the planets orbit at all. Without it, they would simply drift away into the darkness between the stars. The sun is, at its heart, a vast ball of hydrogen and helium held together by its own gravity, and deep within its core, temperatures reach somewhere near 27 million degrees Fahrenheit. Under that kind of pressure and heat, hydrogen atoms fuse together to form helium, releasing enormous amounts of energy in the process. This is nuclear fusion, and it's the quiet engine that has powered the sun for roughly 4.5 billion years. Every bit of warmth that reaches your skin on a sunny afternoon began as a fusion reaction in the sun's core, and then spent an almost unbelievable amount of time, sometimes hundreds of thousands of years, slowly making its way out through the sun's dense layers before finally escaping into space and racing toward Earth in just about 8 minutes. It's strange to think that the light warming your face today started its journey before recorded history began. The sun's surface, the part we can actually see, is called the photosphere, and it's cooler than the core by a wide margin, a mere 10,000 degrees Fahrenheit or so. Above that lies the sun's atmosphere, including a wispy outer layer called the corona, which is, oddly, hundreds of times hotter than the surface below it. Scientists still don't fully understand why the corona is so much hotter than the photosphere it surrounds, and it remains one of the sun's quiet, ongoing mysteries. The sun rotates too, though not all at once the way a solid object would. Because it's made of gas and plasma rather than solid rock, different parts of the sun spin at different rates. Its equator completes a rotation in about 25 days, while regions closer to its poles take closer to 35 days to turn once. This is called differential rotation, and it plays a role in generating the sun's powerful and constantly shifting magnetic field. The same field responsible for sunspots, solar flares, and the beautiful auroras that sometimes dance across Earth's polar skies. Now let's drift a little closer to home, toward the 4 small rocky worlds that orbit nearest to the sun. These are the terrestrial planets, Mercury, Venus, Earth, and Mars, and they share a family resemblance. Each has a solid surface you could, in theory, stand on, unlike the gas giants further out. Each is relatively small compared to the giants beyond them, and each formed in the same hot, crowded region close to the young sun. where only rock and metal could survive the heat, while lighter gases were pushed further out into the cooler reaches of the forming solar system. Mercury is the smallest planet and the closest to the Sun, and it lives an extreme kind of existence because of that closeness. A year on Mercury, the time it takes to complete one full orbit, lasts just 88 Earth days, making it by far the fastest planet in our solar system. But strangely, a single day on Mercury, from one sunrise to the next, takes about 176 Earth days because the planet rotates so slowly on its axis. This means that if you lived on Mercury, you would experience fewer than 2 sunrises in an entire year. Despite being closest to the Sun, Mercury is not the hottest planet. That title belongs to Venus, and we'll get there in a moment. Mercury has almost no atmosphere to hold in heat, so while its daytime temperatures can soar past 800 degrees Fahrenheit, its nights plunge to nearly 300 degrees below zero. It's a world of brutal extremes, swinging between scorching and frozen within the span of a single, very long day. Mercury's surface is heavily cratered, much like our own moon, because without a thick atmosphere to burn up incoming debris, the planet has been struck again and again over billions of years, and those scars remain largely untouched by weather or erosion. Venus, the second planet from the Sun, is often called Earth's twin because of its similar size and mass. But the resemblance ends almost immediately after that. Venus has a thick, crushing atmosphere made mostly of carbon dioxide, with clouds of sulfuric acid drifting through its skies. This atmosphere traps heat so effectively through an intense greenhouse effect that Venus's surface reaches temperatures of about 860 degrees Fahrenheit, hot enough to melt lead, and hotter than Mercury despite being twice as far from the Sun. The atmospheric pressure on Venus's surface is also immense, roughly 90 times that of Earth's, similar to what you'd feel nearly a mile beneath the ocean's surface. Venus has another peculiarity. It rotates backward compared to most other planets, a phenomenon called retrograde rotation, and it does so incredibly slowly. A single day on Venus, one full rotation on its axis, takes about 243 Earth days, which is actually longer than a Venusian year, since Venus orbits the Sun in just 225 Earth days. In other words, a day on Venus is longer than its year, a fact that seems almost impossible until you remember just how strange and varied the mechanics of our solar system truly are. Then comes Earth, our own quiet, blue world, and it's worth pausing here not to recite what you already know about home, but to appreciate a few of the details that make it genuinely unusual. Earth sits in what scientists sometimes call the habitable zone, or more poetically, the Goldilocks zone, the narrow band of distance from the Sun where temperatures allow liquid water to exist stably on a planet's surface. Too close, and water boils away, as it likely did in Venus's ancient past. Too far, and water freezes solid. Earth is also the only planet in our solar system known to host life, as far as we've been able to determine. And it's the only one with liquid water covering the majority of its surface, about 71% of it. Earth's atmosphere is a delicate balance of nitrogen and oxygen, unlike the carbon dioxide-heavy atmospheres of its rocky neighbors. And that balance is maintained in part by the very life that depends on it, in a slow, ongoing exchange between plants, oceans, and air. Earth's magnetic field, generated by the churning molten iron in its outer core, forms an invisible shield that deflects much of the sun's charged particles, protecting the atmosphere from being gradually stripped away, the way scientists believe happened to Mars long ago. Earth's single natural satellite, the Moon, deserves its own quiet moment tonight because it has shaped our planet in more ways than its gentle light suggests. The leading theory of the Moon's formation holds that roughly 4.5 billion years ago, a Mars-sized body, sometimes called Theia, collided with the young Earth. The debris flung into orbit from that collision gradually gathered together under its own gravity to form the Moon. It's a violent origin story for something that now hangs so peacefully in our night sky. The Moon is slowly drifting away from Earth, moving outward at a rate of about 1.5 inches per year, roughly the speed at which your fingernails grow. Billions of years from now, this slow retreat will have real effects, but for now, the Moon remains close enough to exert a powerful pull on Earth's oceans, creating the tides that rise and fall along every coastline. The Moon is also responsible for stabilizing Earth's axial tilt, keeping it fairly steady at around 23.5 degrees, which gives us our relatively stable seasons. Without the Moon's steadying influence, Earth's tilt could wobble far more dramatically over long time scales, leading to much more extreme and unpredictable climate shifts. The Moon has no atmosphere to speak of, which means it has no weather, no wind, no erosion in the way we understand it on Earth. Footprints left by astronauts during the Apollo missions decades ago remain essentially undisturbed today, and will likely stay that way for millions of years, since there's no wind to blow them away and no rain to wash them out. It's a strangely permanent kind of stillness, holding on to moments the way Earth never could. From Earth, we drift onward to Mars, the fourth planet from the Sun, often called the Red Planet because of the iron oxide, essentially rust, and that covers much of its surface and gives it that distinctive rusty hue. Mars is smaller than Earth, with roughly half its diameter, and it has a much thinner atmosphere, composed mostly of carbon dioxide at a pressure less than 1% of what we experience here. That thin atmosphere means Mars struggles to hold onto heat, and its temperatures swing wildly from a relatively mild 70 degrees Fahrenheit near the equator on a summer day to nearly 200 degrees below zero at the poles in winter. Mars is home to some genuinely record-setting geography. Olympus Mons, a shield volcano on the Martian surface, is the tallest known mountain in the entire solar system, standing about 2.5 times the height of Mount Everest. Nearby lies Valle Marineris, an enormous canyon system stretching roughly the width of the continental United States, so vast that if it were placed on Earth, it would stretch from California to the East Coast, dwarfing our own Grand Canyon many times over. There is strong evidence that Mars once had liquid water flowing across its surface billions of years ago, including ancient river channels, dried lake beds, and mineral deposits that typically form in the presence of water. Today, that water largely exists as ice, locked away in the planet's polar caps and possibly hidden beneath its surface. Whether Mars ever supported life remains one of the great open questions of planetary science and the ongoing search for answers through rovers slowly trundling across its dusty plains continues even now tonight as you drift towards sleep. Mars has two small irregularly shaped moons, Phobos and Deimos, thought by many scientists to be captured asteroids rather than moons that formed alongside the planet. Phobos, the larger and closer of the two, is slowly spiraling inward toward Mars, and in tens of millions of years it's expected to either crash into the planet's surface or break apart entirely, potentially forming a faint ring around Mars before that final descent. Beyond Mars lies a wide, scattered band known as the asteroid belt, a region between Mars and Jupiter filled with countless rocky fragments left over from the solar system's formation. Despite how it's often depicted in films, the asteroid belt is not a dense, crowded field of tumbling rocks that a spacecraft would need to dodge and weave through. In reality, it's mostly empty space. The asteroids within it are, on average, hundreds of thousands of miles apart, and several spacecraft have passed through the belt without difficulty, barely coming close to any of its residents. The largest object in the asteroid belt is Ceres, which is massive enough that it's classified as a dwarf planet rather than a simple asteroid. Ceres makes up roughly a third of the entire mass of the asteroid belt on its own, despite having a diameter of less than 600 miles. Beneath its cratered, dusty surface, scientists believe Ceres may hold a significant reservoir of water ice, and some bright, mysterious spots discovered on its surface turned out to be deposits of salt left behind as water sublimated away into space. Past the asteroid belt, the solar system changes character entirely. We leave behind the small, rocky worlds and enter the realm of the gas giants. Enormous planets made primarily of hydrogen and helium with no solid surface to stand on at all. The first and largest of these is Jupiter, and it's difficult to overstate just how immense Jupiter truly is. It's the largest planet in our solar system by a wide margin, so massive that all the other planets combined could fit inside it with room to spare. In fact, Jupiter contains more than twice the combined mass of every other planet in the solar system put together. Jupiter's most famous feature is the Great Red Spot, a massive storm that has been raging in its atmosphere for at least several hundred years, and possibly much longer. The storm is so large that 2 or 3 Earths could fit inside it, although observations over the past century suggest it has been gradually shrinking. Jupiter's atmosphere is a churning, banded pattern of clouds, driven by ferocious winds that can exceed 330 miles per hour, whipping the planet's colorful stripes into constant shifting motion. Jupiter also has an enormous family of moons, more than 90 confirmed so far, with 4 standing out as particularly remarkable. These are the Galilean moons, named after Galileo Galilei, who first observed them through a telescope in 1610. Io, Europa, Ganymede, and Callisto. Io is the most volcanically active body in the entire solar system, covered in hundreds of active volcanoes fueled by the intense gravitational stretching and squeezing it experiences from Jupiter's powerful gravity. Europa, by contrast, is a world of ice with a smooth, cracked surface that scientists believe conceals a vast liquid ocean underneath, warmed by the same gravitational forces that make Io so volcanic. And that hidden ocean makes Europa one of the most promising places in our solar system to search for signs of life beyond Earth. Ganymede, meanwhile, holds a title of its own. It's the largest moon in the entire solar system, even larger than the planet Mercury, though less massive due to its icy composition. And Callisto, the outermost of the 4 Galilean moons, is one of the most heavily cratered objects ever observed. Its ancient surface a record of billions of years of impacts, largely unchanged because it lacks the geological activity that has reshaped the surfaces of its sibling moons. Beyond Jupiter lies Saturn, perhaps the most visually striking planet in our solar system, thanks to its dazzling system of rings. Those rings are made primarily of countless particles of ice, mixed with the smaller amounts of rocky debris, ranging in size from tiny grains of dust to chunks as large as a house. Despite stretching out to a diameter wider than the distance between Earth and the Moon, Saturn's rings are remarkably thin, in most places only about 30 feet thick, an almost impossibly delicate structure on such an enormous scale. Saturn itself is the second largest planet in the solar system, and it's so much less dense than the other planets that, in theory, if you could find an ocean large enough to hold it, Saturn would actually float. Its density is lower than that of water, a strange fact for a planet that outweighs Earth many times over. Like Jupiter, Saturn is composed mostly of hydrogen and helium, and it too experiences powerful winds, reaching speeds of over 1,100 miles per hour. Near its equator, among the fastest winds recorded anywhere in the solar system. Saturn has more than 145 confirmed moons, and among them, Titan stands out as one of the most fascinating worlds we've ever studied. Titan is the only moon in the solar system known to have a substantial atmosphere, thicker even than Earth's, and is the only place beyond Earth where we've confirmed stable liquid on the surface. Though on Titan, that liquid isn't water, but lakes and rivers of liquid methane and ethane, existing at temperatures far below anything survivable for us, but strangely reminiscent of Earth's own water cycle, just built from entirely different chemistry. Another of Saturn's moons, Enceladus, is small but remarkable, venting plumes of water, ice, and vapor from its south pole out into space, evidence of a liquid ocean hidden beneath its icy crust, kept warm by the same kind of tidal heating that warms Europa. These plumes are so significant that some of the material has actually contributed to one of Saturn's fainter rings, a quiet, ongoing connection between a small icy moon and the grand structure that makes its parent planet so beautiful. Further out still, past Saturn, we come to Uranus, an ice giant with a personality all its own. Uranus is tilted almost entirely on its side, rotating at an axial tilt of about 98 degrees, which means it essentially rolls around the sun like a ball, rather than spinning upright the way most other planets do. Scientists believe this dramatic tilt was likely caused by a massive collision, or perhaps a series of them, sometime in the planet's early history. Because of this extreme tilt, Uranus experiences seasons unlike anywhere else in the solar system. Each pole spends roughly 21 years in continuous sunlight, followed by 21 years of continuous darkness. Over the course of the planet's 84-year orbit around the sun, Uranus gets its pale blue-green color from methane in its atmosphere, which absorbs red light and reflects blue and green wavelengths back into space. It's classified along with Neptune as an ice giant rather than a gas giant, because beneath its outer atmosphere, it's believed to contain a thick layer of water, ammonia and methane ices, surrounding a small rocky core. Uranus also has a faint ring system of its own, though far less prominent than Saturn's. Discovered only in 1977, when astronomers noticed the rings briefly blocking the light of a star passing behind the planet. And finally, at the outer edge of the traditional planetary lineup, we reach Neptune, the most distant of the 8 planets and the only one that cannot be seen with the naked eye from Earth. Neptune is a world of astonishing extremes when it comes to weather, and it hosts the fastest winds ever recorded on any planet in our solar system, with gusts reaching over 1,200 miles per hour, faster than the speed of sound here on Earth. It's a strange contradiction, since Neptune receives only about 1/40th of the sunlight that Earth does, and yet somehow generates the most violent winds we know of. Neptune's deep blue color, even richer than Uranus's, also comes from methane in its atmosphere, though scientists believe there may be an additional unknown compound contributing to its striking hue. Neptune has a large moon named Triton, which is unusual because it orbits the planet in a retrograde direction, opposite to Neptune's own rotation, a strong hint that Triton wasn't born alongside Neptune, but was instead a captured object, likely a former resident of the icy, distant Kuiper Belt, pulled into orbit by Neptune's gravity long ago. Neptune was also discovered in a wonderfully unusual way. Rather than being spotted first through a telescope, its existence was predicted mathematically. Astronomers noticed that Uranus's orbit was being subtly disturbed by the gravity of some unseen object. And using those calculations, they determined almost exactly where a new planet should be found. In 1846, astronomers pointed their telescopes to that predicted location, and there was Neptune, waiting almost precisely where the mathematics said it would be. Beyond Neptune lies a realm that often gets left out of the simpler stories about our solar system, but deserves its place tonight. The Kuiper Belt, a vast donut-shaped region of icy bodies stretching far beyond the orbit of Neptune. It's within this region that we find Pluto, once considered the 9th planet, reclassified in 2006 as a dwarf planet, after astronomers realized it was just one of many similar icy worlds scattered throughout the Kuiper Belt, rather than a unique outlier among the 8 true planets. Pluto is small, smaller even than Earth's own moon, and it has 5 known moons of its own, the largest of which, Charon, is so massive relative to Pluto that the two are sometimes described as a double dwarf planet system, orbiting a shared center of gravity that lies outside of Pluto itself. When NASA's New Horizons spacecraft flew past Pluto in 2015, after a journey of nearly a decade, it revealed a surprisingly complex and active little world, complete with towering mountains of water ice, vast plains of nitrogen ice arranged in strange polygonal patterns, and even hints of a possible subsurface ocean. Beyond even the Kuiper Belt lies the Oort cloud, a theoretical, roughly spherical shell of icy debris thought to surround the entire solar system at an almost unimaginable distance, potentially extending nearly halfway to the nearest star. The Oort cloud has never been directly observed. It's simply too far away and too faint. But its existence is inferred from the behavior of long-period comets, icy wanderers that swing through the inner solar system on orbits that can take thousands or even millions of years to complete. Comets themselves are worth lingering on for a moment. These ancient travelers made of ice, dust, and rock, often described as dirty snowballs left over from the very formation of the solar system. As a comet approaches the sun, the increasing heat causes its ices to vaporize, releasing gas and dust that form the comet's glowing tail. And that tail always points away from the sun, regardless of which direction the comet is actually traveling, because it's shaped by the constant outward pressure of solar wind and radiation. Some comets, like the famous Halley's Comet, are short-period comets originating in the Kuiper Belt, returning to the inner solar system on a predictable schedule, in Halley's case, roughly every 76 years, meaning most people are fortunate to witness it only once or twice in a lifetime. Other comets arrive from the distant Oort cloud on journeys so long that a single orbit can outlast entire human civilizations, arcing out into the darkness for millennia before slowly making their way back toward the warmth of the sun. Pluto isn't alone out there in the Kuiper Belt, and it's worth spending a little more time with its quiet neighbors before we drift further. Eris, discovered in 2005, is another dwarf planet, similar in size to Pluto, and for a time thought to be slightly larger, which was actually part of what triggered the broader debate about how to define a planet in the first place. Eris orbits even further from the sun than Pluto on average, taking roughly 558 years to complete a single journey around the sun, meaning it has not yet completed even one full orbit since it was first observed by telescope. Then there's Haumea, an unusual, elongated dwarf planet that spins so quickly on its axis, completing a full rotation in just under 4 hours, that it's been stretched into an egg-like shape by its own momentum. And Makemake, named after a creator deity of the Rapa Nui people of Easter Island, rounds out the group of confirmed dwarf planets, a reddish, icy world that, like its siblings, drifts slowly through the dim light of the outer solar system, far from the sun's warmth. The sun's influence, though, doesn't simply stop at the edge of the planets, or even at the Kuiper Belt. It extends much further, in the form of the solar wind, a continuous stream of charged particles flowing outward from the sun in every direction at speeds that can exceed 1,000,000 miles per hour. This solar wind carves out a vast, bubble-like region of space called the heliosphere, which envelops the entire solar system, planets and all, like a protective cocoon, pushing back against the thin, cold material that drifts between the stars. Eventually, far beyond even Pluto's orbit, the pressure of the solar wind weakens enough that it's overtaken by that interstellar material, forming a boundary called the heliopause. Both Voyager 1 and Voyager 2, launched in 1977, have now crossed this boundary, becoming the first human-made objects to leave the heliosphere entirely and drift into true interstellar space, carrying with them a golden record of sounds and images from Earth, a quiet message sent outward with no expectation of ever being answered. It's worth pausing too on the meteor showers that occasionally light up our night skies, because they connect directly back to the comets we spoke of a little earlier. As a comet swings through the inner solar system, it leaves behind a loose trail of dust and debris along its orbital path. When Earth, in its own yearly journey around the sun, happens to pass through one of these debris trails, tiny particles, most no larger than a grain of sand, burn up in our atmosphere at tremendous speed, creating the brief bright streaks we call shooting stars. The Perseid meteor shower, visible every August, comes from debris left behind by Comet Swift-Tuttle, while the Geminid shower each December has a stranger origin, tracing back not to a comet but to an asteroid-like object called Phaethon, whose true nature scientists are still working to understand. The exploration of this vast system from where we sit tonight has been carried out almost entirely by machines sent outward on our behalf. Beginning in the late 1950s and continuing through today, spacecraft have visited every planet in the solar system at least once. An extraordinary achievement when you consider that the entire endeavor has unfolded within a single human lifetime. The Voyager probes swept past Jupiter, Saturn, Uranus, and Neptune in a single, extended grand tour, taking advantage of a rare planetary alignment that occurs only once every 175 years. Closer to home, rovers have trundled slowly across the dusty plains of Mars for years at a time, and orbiters continue to circle Venus, Mercury, and the outer gas giants, sending back a slow, steady stream of images and data, quietly expanding what we understand about the neighborhood we call home. Earth's auroras, those shifting curtains of green and pink light that sometimes appear near the poles, are far from unique to our planet, and it's worth drifting past a few of the other worlds where similar lights have been observed. Auroras form when charged particles from the solar wind are funneled by a planet's magnetic field down toward its poles, where they collide with atmospheric gases and release soft, glowing light. Jupiter, with by far the strongest magnetic field of any planet in the solar system, some 20,000 times stronger than Earth's, has auroras far more powerful and persistent than our own, generating enormous amounts of ultraviolet light that continuously ring its polar regions. Saturn II has been observed with shimmering polar auroras, captured in detail by the Hubble Space Telescope and later by the Cassini spacecraft during its many years orbiting the ringed planet. Even Uranus and Neptune, despite their unusual and lopsided magnetic fields, tilted at odd angles compared to their axes of rotation, have shown faint traces of auroral activity, glowing softly in wavelengths invisible to the naked eye. Beyond Saturn's famous rings, it turns out that ring systems are more common among the outer planets than once assumed. Jupiter has a faint, thin ring made mostly of dust, likely kicked up by micrometeorite impacts on its small inner moons, far too dim to be seen without a spacecraft passing close by. Uranus has a set of narrow dark rings, first detected in 1977 and later imaged directly by Voyager 2 in 1986, made of particles darker than coal, unlike the bright icy rings of Saturn. Neptune too has faint, incomplete rings, including unusual clumped sections called ring arcs, whose gravitational stability puzzled astronomers for years before it was better understood. Taken together, these fainter ring systems suggest that at some point in their history, all four gas and ice giants likely captured or generated rings of debris, and Saturn's rings, so bright and prominent today, may simply be a temporary, dazzling phase, one that, on cosmic timescales, will eventually fade as the icy particles slowly spiral inward and rain down onto the planet itself. There are, scattered throughout the solar system, a handful of quiet, gravitationally stable locations called Lagrange points, where the combined gravitational pull of two large bodies, say the Sun and the Earth, creates a kind of balanced pocket where a smaller object can sit in a stable position relative to both. These points have become quietly essential to modern space exploration. The James Webb Space Telescope, for instance, orbits the Sun at a location called the second Lagrange point, nearly 1 million miles from Earth, where it stays in a fixed position relative to our planet without needing constant fuel to maintain its orbit. Jupiter, too, has its own famous Lagrange points, occupied not by spacecraft but by thousands of asteroids, known as the Trojan asteroids, trapped in stable clusters that lead and trail the giant planet along its orbit, silent companions that have likely ridden along with Jupiter for billions of years. It's easy, drifting through all of this, to imagine our solar system as something unique. But astronomers have now confirmed the existence of thousands of planets orbiting other distant stars, worlds called exoplanets, ranging from scorching gas giants far larger than Jupiter to small rocky planets not unlike our own. None of them are close enough to visit or even to see with any real clarity, but their existence quietly reframes everything we've explored tonight. Our sun, our 8 planets, our rings and moons and ancient icy comets are not some singular exception in the universe, but rather one ordinary example of a pattern that seems to repeat itself quietly, again and again, around countless other stars scattered through the dark. It's worth taking a slow, unhurried look forward to, at where all of this is eventually headed, though the timescales involved are so vast that there's no need for any real concern tonight. The sun, like all stars, has a finite supply of hydrogen fuel at its core, and in roughly 5 billion years, that supply will begin to run low. As it does, the sun will start to swell, cooling and reddening as it expands into what's called a red giant, growing so large that it will likely engulf Mercury and Venus entirely, and possibly reach as far as Earth's current orbit. Long before that final expansion, though, the sun's gradually increasing brightness, even over the next billion years or so, is expected to slowly heat Earth's surface, eventually boiling away its oceans in a slow, quiet echo of whatever happened to Venus so long ago. After its red giant phase, the sun will eventually shed its outer layers into space, forming a brief, glowing shell of gas called a planetary nebula, while its core collapses down into a small, dense, slowly cooling ember known as a white dwarf, roughly the size of Earth, but containing much of the sun's original mass. It will simply sit there afterward, radiating away its remaining heat for trillions of years, far outlasting any of the planets that once orbited it in their current form. It's a strange kind of comfort in a way, knowing that these changes unfold over timescales so vast they're almost meaningless to a single human life, or even to the entire span of human history so far. Tonight, and for a very long time to come, the sun will simply keep rising, keep setting, keep quietly holding its planets in their steady, familiar orbits. It's also worth remembering gently how recently we came to understand any of this at all. For most of human history, people believed Earth sat motionless at the center of everything, with the sun, moon, and stars quietly circling around it. It wasn't until the 16th century that the astronomer Nicholas Copernicus proposed a different arrangement, placing the sun rather than the Earth at the center of what we now call the solar system. A quiet, radical idea that took generations to be fully accepted. Galileo Galilei, peering through one of the very first telescopes in the early 1600s, found direct evidence supporting this new view, observing moons orbiting Jupiter rather than Earth, proof that not everything in the heavens circled our own small world. And it was Johannes Kepler, working with decades of careful observations, who who finally worked out that planets don't move in perfect circles at all, but in gentle ellipses, tracing smooth, curved paths around the sun that we still use to precisely predict their positions today, centuries later. Stepping back from all these individual worlds, it's worth considering gently how this entire system came to be in the first place. The prevailing scientific understanding is that the solar system formed roughly 4.5 billion years ago from a vast, slowly rotating cloud of gas and dust called the solar nebula. Something, perhaps the shock wave from a nearby exploding star, caused this cloud to begin collapsing under its own gravity. As it collapsed, it spun faster and flattened into a disk, with the vast majority of its material gathering at the center to form the sun. The leftover material in that spinning disk gradually clumped together through countless small collisions into larger and larger bodies. First tiny grains of dust, then pebbles, then boulders, then planetesimals, and eventually the planets we know today. Closer to the young hot sun, only rock and metal could survive, forming the small terrestrial planets. Further out, past what's called the frost line, it was cold enough for ices to remain solid, allowing much larger planets to form by gathering enormous amounts of gas around their icy cores. The origins of Jupiter, Saturn, Uranus, and Neptune. This process wasn't gentle or orderly. Early in its history, the solar system was a chaotic, violent place, with young planets colliding, migrating through their orbits, and scattering smaller debris in every direction. Some scientists believe that Jupiter and Saturn in their early years may have shifted position dramatically, an event sometimes called the Grand Tack, which could have reshaped the entire architecture of the inner solar system before everything gradually settled into the relatively stable, orderly arrangement we observe today. And it does remain, for the most part, remarkably stable. A vast, quiet clockwork of orbits that has held steady for billions of years, with planets circling the sun in the same directions, along roughly the same flat plane, like marbles rolling gently around a shallow bowl. It's a stability that allowed, on at least one small blue world, enough time and enough calm for something as unlikely and precious as life to take hold, evolve, and eventually look up at the night sky and wonder what it was looking at. It's worth remembering, too, just how much empty space surrounds all of this. If you shrank the sun down to the size of a large beach ball, Earth would be a small pea, orbiting nearly 200 feet away, and Neptune, the outermost planet, would be more than a mile distant. Even our closest neighboring star, aside from the sun, is so far away that light from it takes over 4 years to reach us. The distances involved are almost impossible to hold in the mind, and yet here we are, on one small world, quietly orbiting one small star, in one small corner of a solar system that is itself only a tiny fraction of a single galaxy among billions. As we drift toward the end of tonight's journey, let's take one last, slow pass through everything we've traveled past. We began at the sun, a churning furnace of nuclear fusion, ancient and enormous, holding the entire system together with its gravity. We passed Mercury, scorched and cratered, and Venus, hidden beneath its thick, poisonous clouds. We paused at Earth and its quiet companion, the Moon, born from a violent collision but settled now into a peaceful, stabilizing orbit. We crossed the rusty plains of Mars, home to the tallest mountain and the deepest canyon in the solar system, and drifted through the scattered rubble of the asteroid belt. We marveled at Jupiter, so vast that all the other planets could fit inside it, and its ocean-hiding moon, Europa. We admired Saturn's impossibly thin rings and the strange methane lakes of Titan. We tilted sideways with Uranus, rolling through its 84-year orbit, and felt the fierce winds of distant Neptune, the planet discovered through mathematics before it was ever seen. We reached the icy edge of the Kuiper Belt, where Pluto and its moon Charon danced together, and gazed in our imagination toward the almost mythical distance of the Oort cloud, where ancient comets begin their long, slow journeys home. And so tonight, we leave the solar system exactly where it has always been, quietly turning, planet after planet, moon after moon, held together by the steady, patient pull of a single star, doing tonight exactly what it has done for 4.5 billion years, and what it will likely keep doing for billions more. There's something quietly comforting in that kind of permanence, in knowing that whatever happens down here, on this small blue world, the sun will rise again tomorrow. The moon will keep its gentle, steady orbit. And out beyond the reach of any telescope, the ancient comets of the Oort cloud will still be drifting slowly through the dark, patient and unhurried, the way they have been since long before you were born, and the way they'll continue long after tonight fades into memory. You've drifted tonight through the fire of the sun, the crushing heat of Venus, the quiet stability of Earth and its moon, the rust-colored plains of Mars, the storms of Jupiter, the rings of Saturn and the sideways tumble of Uranus, the howling winds of Neptune, and out to the icy ancient edges of the Kuiper Belt and beyond. You've traveled further tonight than any of us ever could in waking life, and you've done it without ever leaving the comfort of where you're resting right now. Let it hold you now, the quiet, steady turning of all those worlds, spinning gently in the dark, asking nothing of you except to rest. Sleep well, and I'll see you next time for another 100 facts drifting softly into sleep.